All right, well, once again, it's my pleasure to come before you and show you how creation confirms what the Bible teaches, that the physical universe is consistent with what we'd expect. And in this case, we're going to dive into an area of creation that most people haven't even thought about. And there is a secret code built into this aspect of creation that I submit has no secular explanation whatsoever. There is no basis for it. You cannot make sense of this in anything other than the Christian worldview. We can make sense of this. Now, if you really understand the presuppositional apologetic that we have been expositing and applying in this conference, you'll understand that really that's true of any evidence, really. But this one is especially neat because I haven't even heard any good rescuing devices for what I'm about to present to you. There is a secret code built into numbers. Numbers, 1, 2, 3, 4. What if we found a code built into them? What would that indicate? Codes indicate intelligence. We don't think about numbers being created, but God did create them in the sense that He's responsible for them. His mind is responsible for numbers. They're not the same as other things God created, but He is responsible for them. And therefore, there is intelligence built into numbers and the laws of mathematics that express the relationship between numbers. And this code was discovered in the 1980s. This is a fairly recent development. I am older than this discovery, and that's kind of neat. So that's pretty amazing, I think, in the history of science when we consider these things. And as with many things, we have to deal with some difficult things first before we get into the really neat stuff. It kind of reminds me of when I was a little kid and my mother would prepare these wonderful meals. She's a very good cook, but every now and then she'd make something I didn't like broccoli. Yuck. And now, some of you like broccoli, and there's grace to cover that, and cheese, but because that does help. But yeah, sometimes in moments of rare maturity, when I was a kid, I would eat the broccoli first, get that out of the way, so that I could then enjoy the rest of the meal, because you had to eat everything on the plate, right? So in that same spirit, we got a little broccoli to do first, but stay with me because it's going to get really good, okay? We're going to begin with definition of set. The set in mathematics is a collection of elements, in this case, a collection of numbers with a common defined property. A common defined property. And so in most sets of numbers, some numbers are included while other numbers are excluded. Some numbers belong to the set, other numbers don't. This is pretty clear. For example, if I said consider the set of even numbers, then these numbers would belong to that set, and the other numbers that you see there would not belong to that set, right? And you can tell just by looking at it whether the number is even or not, because if it ends in 0, 2, 4, 6, or 8, it will be divisible by 2 and result in an integer. That's a set. Some numbers belong to it, other numbers do not belong to it. I could say consider the set of negative numbers, in which case these numbers would belong and the other numbers would not. Some numbers like -2 belong to both sets. They're both even and also negative. So those are both examples of sets. And so some numbers are included, some numbers are not included. And these particular two sets that we've just talked about are pretty easy because you can tell just by looking at the number whether or not it belongs. In this case, if you see a little negative sign in front of it, it does belong to the set of negative numbers. But there are other sets where their definition is a little more complicated, and you can't tell just by looking at the number whether it belongs. You have to do a little bit of work to figure it out. And we're going to talk about one of those sets. It's called the Mandelbrot set. It's a set of numbers, and it's defined by that little phrase that you see there, such that you're going to have to do some work to figure out if a number belongs. The Mandelbrot set is defined as the set of all numbers C. C represents a number that's potentially a member of the Mandelbrot set, for which another number, Z, remains small according to this little formula. And Z is in fact not just one number, but a string of numbers. That's what the little n means. That means there's a Z1, there's a Z2, there's a Z3, there's a Z4. Each one of them is like a mailbox that contains one number in it. And the next value of Z, the Zn plus 1, the next mailbox over, is related to the previous mailbox by squaring it and then adding C. That sounds complicated, but it's actually very simple, and I'll give you some illustrations of this. But basically, when you plug a number C into this formula to test whether or not it's a member of the Mandelbrot set, one of two things will happen. That sequence of Z that's generated will either get bigger and bigger and bigger and bigger and bigger, or it won't. It'll kind of stay small. If it stays small, C is a member of the Mandelbrot set. If the sequence of Z gets really big without limit, then C is not a member of the Mandelbrot set. That's the rule, okay? So if the sequence of Z stays small, C is a member of the Mandelbrot set. If the sequence gets really big without limit, then C is not a member of the Mandelbrot set. Let's do a couple of test cases here. So we're going to ask, is the number 1 part of the Mandelbrot set? So C in this case is 1. That's the number we're checking to see if it belongs. And so we're going to put that in for C. So we get Z squared plus 1 is the next value of Z. Okay. Now, by definition, the first Z starts as 0. That's just part of the definition there. So Z sub 0 is 0. So we're going to put that in for Z sub n. So we have 0 squared. 0 times itself is 0. Plus 1 would be 1. Yeah. 0 plus 1 is 1. And so that is the next value of Z. Okay. And so we're going to keep track of that. And since that's the new value of Z, we're going to put that back in the formula. So now we have 1 squared, which is 1, plus 1 is 2. So that's the next value of Z. We're going to put that back in. Okay. 2 squared would be 4, plus 1 would be 5, right? It's going to put that back in. And we'll do it again. 5 squared, that'd be 25, plus 1 is 26. Going to put that back in. 26 squared plus 1 is a big number, and so on. Okay. Now, do we have to do any more to see what's happening? No. We can see what's happening. Is Z staying small? No. So is the number 1 part of the Mandelbrot set? No. You got it. Okay? That's how you do it. Easy. Tedious, but easy. Okay? Let's try another one. Let's try negative 1. So is negative 1 part of the Mandelbrot set? So now we're going to put in negative 1. That'll be Z squared minus 1 is the next value of Z. Z always starts as 0. So we'll put that in. So now we have 0 squared, which is 0 minus 1 is negative 1. So we'll put that back in. That's the new value of Z. Negative 1 squared is positive 1. Minus 1 is 0. Oh, that's interesting. Put that back in. 0 squared minus 1, negative 1. Oh, you see what's happening? 0, negative 1, 0, negative 1, 0, negative 1. Is the sequence of Z staying small? Yes, it is. So is negative 1 part of the Mandelbrot set? Yes, it is. There you go. Okay, that's how you do it. You just have to run it through that little formula. You have to do it a few times to kind of see what the pattern's going to be. And that's all there is to it. Well, there is one more complication. One more complication. And then it's going to get really good. Stay with me. It's going to get really good. Okay? Got to do the broccoli first. The Mandelbrot set also includes what are called complex and imaginary numbers. Have you heard of these? I hate the name because an imaginary numbers makes it sound like something we made up. It's not something we made up. These do exist. It's just a name, okay? It's just a name. An imaginary number is a number that when you multiply it by itself, you get a negative number. And the sort of the prototypical imaginary number is abbreviated by a lowercase I. And by definition, I squared equals negative 1. And that's a little hard for us to comprehend. Because how can you have a number that when you multiply it by itself, it's negative? Imaginary numbers can't be positive because a positive number squared is also positive, right? Imaginary numbers cannot be negative because a negative number squared is also positive. And imaginary numbers can't be 0 because 0 squared is 0. So how do I make sense of a number that's not negative, not positive, and not 0? That's a little perplexing, isn't it? And that might make you a little uncomfortable. But frankly, when you were a little kid, negative numbers made you uncomfortable, right? Because when you're first exposed to them, I can understand how I can have 2 apples or 3 apples or 5 apples, but how can I have negative 6 apples? That doesn't make any sense, right? When you're a little kid. And then you get a little bit older, you get a bank account, and suddenly negative numbers, they make a lot of sense, right? Yeah. We have experience with negative numbers, and so we're comfortable with them. Imaginary numbers, it's just most adults have never had a lot of experience with them, and so we're a little uncomfortable at first. But I assure you, they do exist, despite the name. And to add insult to injury, those numbers that are not imaginary are called real. It's just a name, okay? But how do we picture a number that's not positive, not negative, and not 0? Well, consider the number line. Okay, so there's the number line all the way out from negative infinity to positive infinity. And numbers that are to the right of 0 would be positive. Numbers that are to the left of 0, those would be negative. Where do we put a number that's not positive, not negative, and not 0? How about up there? It's not to the right of 0, it's not positive. It's not to the left of 0, it's not negative, and it's not 0. You can think of the imaginary numbers as being along a different axis. And by multiplying I, which is the square root of -1, by any real number, you can get other imaginary numbers like half I and negative I and so on. So think of the imaginary numbers as being along the vertical axis and the real numbers as being along the horizontal axis. And the other thing is you can have what are called complex numbers. A complex number has a real part and an imaginary part. And they're off axis, like the number 1 plus 1/2 I is a complex number. It's complex because it has two parts. It has a real part and an imaginary part. And again, those are just names. They both exist. Imaginary numbers exist just as much as the so-called real numbers. I do have to point that out. Just a name. Now, the neat thing about complex numbers is you can represent any point on a plane with one number. You can use the real portion of that number to indicate how far to the left or right, and you use the imaginary portion of that number to indicate how far up and down. So that's it. Imaginary numbers, complex numbers, very useful in a two-dimensional surface. In fact, there's certain problems in physics, as long as they take place in 2 dimensions, you can solve them using complex numbers. That's something that I learned how to do in grad school. It was really very interesting. Now, the Mandelbrot set also includes these complex and imaginary numbers. Okay, and so we can, and it's the same thing. You take that number like 1 plus half I, and you run it through that formula, and Z will either stay small or it'll get big. If it stays small, the number is part of the Mandelbrot set. If it gets big, it's not. And the reason mathematicians were interested in this is because you can't tell just by looking at a number whether or not it belongs. And so they were wondering, is there a pattern? Is there some kind of pattern to the Mandelbrot set? And it turns out there is. And they discovered this pattern by having a computer run through and check these different points, because computers can do this very quickly and see whether that sequence gets big or stays small. And we'll make a map. We'll plot on this chart here whether numbers do belong or don't. Those numbers that do belong to the Mandelbrot set, we'll color those black. Remember we checked -1 and we found that the sequence of Z stayed small, so we'll color it black. Had we checked 0, we would find it also belongs, so we'll color it black. And as we check more and more points, we find that all these numbers do belong to the Mandelbrot set. And again, the computer's going through, checking each number, running it through that little formula, and it finds that the sequence of Z stays small, marks it as black. Numbers that do not belong to the Mandelbrot set, we'll give them a different color, like red. And remember, we checked the number 1, and we found that sequence of Z got really big, really quick. So it does not belong. And if we check these other points, we would find they also do not belong to the Mandelbrot set. And interestingly, a pattern starts to emerge. What's that going to be? What's that going to look like? Well, as we check more and more numbers and have the computer check the points at finer and finer resolution, the shape that emerges is this, amazingly. What you're looking at there is a map of which numbers belong to the Mandelbrot set in black. And if they don't belong, I give them a color like red. And I shaded it to where if the sequence of Z gets really big really fast, I made it like a dark red. If the sequence of Z gets big but does so slowly, I made it a brighter color like yellow. So points that are yellow are really close to the Mandelbrot set, but they're not on it. The points that are black are the points that do belong to the Mandelbrot set. And so you can see we don't have to run through that formula now because the computer's already done it. And so I can ask, does 1/2 I belong to the Mandelbrot set? And you can see it does because it's colored black. The computer's checked that for us. So pretty interesting. And then if I remove the graph so you can see the shape here, really surprising. No one was expecting that when you make a map of which numbers belong to the Mandelbrot set, it would have that incredibly weird shape. But there it is. And you'll notice sort of 3 main features of this. The largest feature is that big heart-shaped feature that's called a cardioid, because it's like a heart. And a cardioid is the shape that you get when you take a circle and roll it around another circle of equal size, keeping your pencil affixed to the one point on the primary circle. See, that's a cardioid. And you can see that is exactly the shape of the main portion of the Mandelbrot set. Why that is, I have no idea, but that is what it is. I'm sure there's a reason, I just don't know what it is. And then the next shapes you might notice are these perfect circles that grow off of the cardioid. The big one is just to the left of the cardioid right there. And there's one at the top, one at the bottom, and other smaller circles, and circles that grow off of those circles. So it has a cardioid, it has one cardioid, and then it has a bunch of perfect circles that grow off that. And then finally, the other feature that you'll see are these little squiggly lines, these little antennae that sort of point away. And one of them is perfectly straight, and that's the sort of the tail that you see right over there on the left side. So pretty remarkable. We'll find that we can zoom in on this shape because we can have the computer check points at finer scales. So we can zoom in on it, and we find that the Mandelbrot set, or rather the map of the Mandelbrot set, has some very interesting properties. For example, you see that top circle. It has a little antenna that branches off and then branches into two for a total of 3, including the trunk. Okay, you see that? 1, 2, 3. Three branches, including the trunk there. Now the next one to the left, if you count the branches on that one, it's 1, 2, 3, 4, 5. Interesting. And the next largest one down is 7. And the next one is 9, 11, 13, 15, 17. All the odd numbers. All the way down to infinity, odd infinity, I guess. So that's kind of weird. So the Mandelbrot set knows how to count by, it knows all the odd numbers somehow. And if you go to the other side, the right side, it's all the numbers, evens and odds. So somehow the Mandelbrot set knows how to count. It's got growing off of these circles, these little antennae that then branch, and they branch mathematically to where each bud has on the right side, each bud has 1 more than the previous, and on the left side, it has 2 more than the previous. Really remarkable. Nobody was expecting that you would get a shape like that at all, let alone that it would somehow know how to count. What's even more remarkable, not only does it know how to count, it knows how to add. Because if you take 5 and 3, you get 8. And lo and behold, that is exactly how many the one in between, the 3 and the 5, have. So if you count the number of antennae on this one, 1, 2, 3, 4, 5, 6, 7, 8, which is 3 plus 5. And that's true of all of them. You pick any, you take any 2 circles, you look at the next largest one in between them, and it will add the number of antennae on the 2. Any of them. Amazing. So somehow this shape, which is not even, I mean, it's not even physical. You can't touch this. It's built into numbers, and somehow it knows how to add and count. Pretty amazing. I mean, it is a mathematical shape, but still, it's pretty remarkable. One of the most fascinating aspects of the Mandelbrot set, though, is what I'm going to show you at this point. I think this is amazing. Because you notice if you look at that little tail on the left there, you'll notice it has a little black spot on it. And we can zoom in on that to see what that looks like. And we find when we zoom in on it, it looks like another Mandelbrot set. Isn't that fascinating? It's almost an exact replica of the original, almost identical, other than it has extra spikes growing off of it that the original parent did not have. We zoomed in on a spike, and the baby version had extra spikes. That's interesting. There's a reason for that. And you'll notice that this little baby Mandelbrot set also has a little black spot on it. What could that be? Well, we'll zoom in on that, and we'll find it's another one. Wow. And that one has spikes, and it's got spikes growing off of the spikes too. So that's interesting. Oh, look, it's got a little bud there as well. And there it is. You could do that for the rest of your life. You could do that for the rest of eternity. There's an infinite number of babies built into the Mandelbrot check, built into the main Mandelbrot set. Isn't that fascinating? Shapes that do this, shapes that have a smaller version of the entire shape built into themselves, are called fractals. And so the Mandelbrot set is an example of a fractal, one of the earlier ones that was found in terms of this type of mathematics. But look how small this baby is compared to the original when we zoom back out. Just gives you a little window into what it must be like to think the way God thinks, right? It's just a little taste of it, because you're like, well, yeah, that blows my mind. Yeah, that's the point. Yeah, it blows my mind too. And not only does the overall shape repeat, but you'll find that sections of the shape also, you think it's going to stop, because man-made objects, you zoom in on them enough and eventually they're smooth, right? But this shape continues to be complex forever. It's infinitely wiggly. It's as wiggly as is possible in 2 dimensions, if that makes any sense to you. It's true. And so you zoom in and you keep zooming in and you think it's going to end, but it just doesn't. It goes on literally forever. But we don't have an infinite amount of time. So we'll examine some of the main features of this shape. One of the interesting places to explore is the valley that takes place between the main cardioid and the main disc. And so we're going to zoom in on that. Mathematicians like to give names to these things. They call this the Valley of the Seahorses, because on the right side it resembles kind of upside down seahorses. They're really rather fascinating. Now, by human convention, points that do belong to the Mandelbrot set are always colored black. Points that do not belong, you can give them any color you want, but it's helpful to shade them such that points that are bright are very close to the Mandelbrot set. So we'll change the color scheme every now and then just to keep things interesting. We can always do that. The colors we choose are arbitrary. The shape, however, is built into numbers. And I'm going to suggest it's built into numbers by God, that we're seeing a little window into the mind of God when we do this, because there is no other way to account for it. I'm giving you a little bit of a spoiler, but that's what it is. So here's one of these seahorses, upside down seahorses, really quite beautiful. Now, again, points that are black do belong to the Mandelbrot set. That's all these points over here on the right and this circle. Points that do not belong, I've given a darker color, like blue. And if they're very far away, dark blue. If they're close to being on the Mandelbrot set, bright blue. And you might say, but wait a minute, there's bright blue down there, and it doesn't look like it's close to the black. But it is. You see, there's actually a very thin black thread that goes out and wiggles around and makes all that shape. So even though you're not seeing it because it's smaller than a pixel, there is a very thin black thread that goes out and wiggles around and makes that complicated shape. And amazingly complicated. No one was expecting that. No one was expecting that when you check to see which numbers belong to z squared plus c, you'd get something like that. This was amazing, which is why this was discovered in the 1980s. That was the first time computers were fast enough to be able to do these calculations repetitively and relatively quickly. And of course, we can do much better now because computers are so much faster than they were in the 80s. If we zoom in on the center of that seahorse, I found that you have this sort of spiderweb type pattern. And I found from experience, you can zoom in on the center of that forever and it doesn't change. It's just a smaller version of the entire web. So that spider web is actually infinitely small. It zooms in to infinity or zero, or I don't know how you want to think about that. But if you go off to the side, I want to go off to the side to see what the spider web is made of, what the threads are made of. So we'll go off to the side here. And it turns out they're made of smaller spider webs. So webs made of smaller webs that are made of smaller webs. That's pretty remarkable. And this is kind of interesting because we have here sort of two central hubs. We have the center of a spider web up at the top and another one down at the bottom. And in between, it looks like they collide. And you actually have 1, 2, and then you see there's actually 4 in the middle and then 1 in the center of that. So it goes from 2 to 4. And as we zoom in, it'll go from 4 to 8 to 16 to 30. It's all the powers of 2, interestingly. And when we zoom in on the center, this is rather remarkable. You can see it going from, oh, look at the middle. How about that? There's another baby hiding in there. How about that? So you can see it's another baby version of the Mandelbrot set. But we zoomed in on a spider web, and the baby version has lots of spider webs growing off the exterior. So that is a common feature of the Mandelbrot set. When you zoom in on a baby, it will inherit the properties of the parent, of the section of the parent that it grows off of. So pretty remarkable. And by the way, you'll notice, not that I'm going to zoom in on it, but it does have a little blob at the end of the tail there too, which is an even smaller version. So, and this one is also infinite because you could zoom in. It's got a valley of seahorses as well. You could zoom in on that and zoom into to a seahorse valley within the seahorse valley, and so on. Gives you a little window into the mind of God. And look how tiny it is compared to the original when we zoom back out. Just tiny. It's just a map. It's just a map of z squared plus c when you run numbers through it. Who could have imagined that numbers would have such complexity and beauty within them? Let's go back to Seahorse Valley. We went off to the right side last time. Now we'll go off to the left side. The left side, it's called the Valley of the Double Spirals. So there you'll see a beautiful double spiral. It reminds me of like a spiral galaxy because they look like that. And you'll see two independent strands that wrap around each other and make that beautiful shape, really stunning. And so we'll zoom in on a thread of it to see what it's made of, and we'll find it's made up of spider webs and smaller spirals as well. And these little shapes here, I call them bow ties. They remind me of a little bow tie because there's, I don't know, just about the right size. And it goes from 2 to 4 to 16. There's the 4, 1, 2, 3, 4, and the next one's 8, and then 16. There's little spirals that grow around it. And of course, in the middle is another baby Mandelbrot, amazingly. Yeah, isn't that beautiful? That's built into numbers. It's always been there. It's been there since creation. It's just only recently have we had the technology to discover that these beautiful shapes are built into math. Kind of makes you wonder what other little surprises God has out there for us that we're still 1,000 years away from discovering. Pretty amazing. Our ancestors had no idea that such shapes were built into math. Nobody did until 1980s. And then an IBM programmer named Benoit Mandelbrot, he began experimenting with this and studying it, and hence the name, the Mandelbrot set. Another valley that's fun to explore, I find the valleys tend to have the really pretty structures in them. So another one is the valley on the end of the cardioid over there to the right. And this one they call Elephant Valley, or Valley of the Elephants. And when we zoom in on it, you'll see why. It's the only symmetric valley where the top and the bottom are mirror images of each other. And you can see, especially when you look at the bottom rung there, I mean, at first it looks like a zipper, but then when you look at the little modules there, they look like little elephants marching one after the other. Let's zoom in on a couple of them here so you can see that. Isn't that interesting? Like an elephant with a really curled up trunk. And there's one elephant on each circle, so you can see a circle there, and it's got an elephant growing off of it, and a circle there, and an elephant growing off of that. There are an infinite number of them. If you zoom in into that valley, you'd think, well, the space in that valley is finite, yes, but the elephants get smaller and smaller and smaller to the point you can actually pack an infinite number of them into finite space. So it's really strange. So an infinite number of elephants. Keep that in mind because we're going to come back to that later. It's important that there's an infinite number of little elephants. And the farther into the valley you get, the curlier their trunk gets, interestingly. So I thought I'd zoom in on that curly trunk. It's a single spiral. It's one strand that wraps around itself, unlike the double spirals we saw earlier. And as we go into that, you can see it again has these sort of little bow tie features. There we go. There's one of them there. And they're comprised of single spirals this time. And again, it goes from 2 to 4 to 16 and so on. You can see the primary 2 there, 1, 2. And as we zoom in, it goes to 4, 1, 2, 3, 4. And then 8, 16, 32, 64, all the way in. And then again, you're not surprised now. You're expecting it. I've kind of learned how to find the baby versions in the Mandelbrot. You just have to look for where two spirals kind of collide in the middle. And inevitably, there will be a little baby Mandelbrot in there. But again, let me remind you that all this structure that you're seeing around it is where there's a very thin black thread that runs out and wiggles around and splits and makes all that complicated shape. So the beauty of these things, I think, is absolutely remarkable. Who could have imagined? I mean, a lot of you that's, oh, well, math, that's a hard subject. It's beautiful because math is the way God thinks about numbers. And of course it's going to be beautiful. We couldn't see it until recently. Isn't that interesting? And again, I'm going to suggest that secularists don't really have any explanation for this at all. They can't make sense of it in their worldview. But I have to also point out that although there are an infinite number, there's an infinite number of baby Mandelbrots in this. And each of those has an infinite number. Because remember, you could zoom in on the tail of that, and sure enough, there's a little baby version there. So just in the tail of this little guy, there's an infinite number of baby Mandelbrots. But there's also an infinite number of these in the main Mandelbrot. So it's not just infinity, it's an infinity of infinities. And so that gives you a new appreciation for the mind of God. We knew he was infinite, but apparently he's infinitely infinite. Yeah, there are different infinities, believe it or not. Mathematicians study these things. And some are bigger than others. It's mind-blowing to me too. But I hope it produces, if nothing else, a little bit of humility before your Creator. What a mind. to think of all this. Always been there. God has been aware of this shape from eternity past. But humans have only discovered it. And we've only scratched the surface because it's infinite. You could spend the rest of your life exploring that shape and you would not have scratched the surface because it's infinite. You can zoom in forever. It's not made up of atoms. Physical things, we zoom in and we get to atoms, and then, there's protons and neutrons and then quarks, and we think that's kind of it because they kind of turn into waves at that point. But this, you could zoom in forever, and it will continue to have structure. And you can even Google zooms where they've zoomed into the Mandelbrot set a Google times, right? 10 to the power of 100. It's just astonishing. You could spend the rest of your life studying that shape. But that is simply one set. One set. It's simply the equation z squared plus c. And that made me think, what happens if you change the equation? What if we do z cubed plus c? You get a different shape. Interesting. Now we've got another set to explore, right? Because it's not good enough that we have this. I mean, this is only infinite. Well, it's only infinitely infinite, but I want more. So now we have another shape, but is it fractal? So this is e cubed plus c, and the main shape there is now, instead of a cardioid, it's a nephroid. A nephroid is what happens when you take a circle half the size of the original and roll it around on the original circle. That's a nephroid, and you can see that is the exact shape of this new, let's call it a multibrot, because it's a multiple of the Mandelbrot. It's also interesting, too. I can change the power gradually from z squared to z cubed. I can do z to 2.1, 2.2, 2.3, 2.4, and animate it. And you can see how one shape morphs into the next. This was kind of a fun little thing to try. Isn't that interesting? So you can see how the Mandelbrot, I'll run it back and forth. So you can see how the Mandelbrot morphs into this multibrot. Isn't that interesting? Everything kind of gets doubled. Some things get quadrupled. But the Mandelbrot, which has one valley on the main shape and no valleys on the circle, now becomes a nephroid, which has two valleys on the main shape and one valley on each of the surrounding shapes. So everything kind of goes up by one, which kind of makes sense. We go from z squared to z cubed. What aspect of it is least changed? What do you think, as you watch it morph from one to the other? I think the Valley of the Elephants on the right side there, right? I think that's the least changed, is right there. And so that made me wonder, does this thing still have elephants? Because the Mandelbrot set has elephants there. What happened to them? Let's find out. Let's zoom in on it. Do we still have elephants? We do still have elephants. Let me zoom in. There they are. How about that? So this multibrot also has elephants. But I want you to notice something. The circles that were on the Mandelbrot, because remember, on the Mandelbrot set, each elephant was standing on one circle. The circles have split into cardioids, and there's now two elephants on each one. So the circles split into cardioids, and the elephants doubled, which is interesting, because remember, previously we had an infinite number of elephants, and now we have twice that many. Isn't that just neat? I mean, that's just, it blows my mind. If you're thinking, how do I understand doubling infinity? I don't know. I don't know. These are the mysteries of God, I suppose. You think it'll still have those little bow tie features? It does, but they've grown an extra leg now. They're now fidget spinners, right? They got 3 now instead of 2. Isn't that fascinating? And if we zoom in on the very center, we have a baby version of this new multibrot. There's the original. There's the baby. Almost identical, except you got the extra stuff growing around the perimeter. Isn't that fascinating? So again, this is also fractal because it repeats itself infinitely. And you could spend the rest of your life studying this shape and you'd never scratch the surface because it is infinite and it's infinitely infinite. Because each of these babies has an infinite number of babies. And so, okay, but still I want to see more. I want to see more. So what happens if I change the formula again? Z cubed, what about z to the 4th? Well, then you get that structure. Oh, okay. Z to the 5th, Z to the 6th. See, it keeps increasing by 1. Z to the 7th makes snowflakes. That's kind of neat. It's one, the number, the sort of symmetry there is 1 less than the power. So Z to the 7th gives you a 6-fold symmetry. And if you zoom in on it, do you get more snowflakes? Yes, you do. How about that? I tried negative powers then. A negative power, like Z to the -2, would be the reciprocal of Z squared. So it's 1 over that. And what that does is interesting. It gives you a different kind of fractal. It flips the thing inside out, because remember, black means the points do belong to the set, and colored means they do not. So in this case, the black is the entire universe. Most of the universe does belong to this set, except a little section in the interior that does not belong. And that's where you get the colored points. And they look like these wonderful little overlapping pebbles. So it's a different kind of a structure. Isn't that beautiful? It's still two-dimensional, but it looks kind of three-dimensional because of the way we perceive an object obscuring an object that we think is behind it. Is it fractal? Well, the overall shape doesn't repeat because it's inverted, but the basic structures do repeat. You get these little pebble shapes no matter how much you zoom in. You get pebbles made of smaller pebbles, made of smaller pebbles, made of smaller pebbles. To infinity. Isn't that stunning? Kind of hypnotic, isn't it? So that's z to the negative 2. Here's z to the negative 3, z to the negative 4, z to the negative 5. That's a way to make inverted snowflakes. It's just amazing the beauty that God has built into numbers that we didn't even know about for 6,000 years until we were very blessed to, 40, 45 years ago, discover these. Isn't that stunning? Built into math. Okay, but what does all this mean? Okay, we've seen some pretty shapes, but is this in any way relevant to Christianity? Yes, it is. Yes, it is. What causes the beauty in fractals is the question I'm going to ask, and also what causes the complexity in fractals. How do we account for this? How do we make sense of it? Well, first of all, what causes the beauty in fractals? I mean, these incredible, stunning shapes. Is it the man-made color scheme? Because I chose the colors. And there are some computer programs where they pick really bad colors, and shame on them, because these are beautiful shapes and they deserve to be treated respectfully, right? But the fact is, the colors don't really create the beauty. I think they bring it out, they enhance it. But even if I make this grayscale, the shape, there's something about the shape that is just beautiful, isn't it? You can take away the color, it's still beautiful. So it's not the man-made color scheme. I think that adds a little bit, like adding salt to food brings out the flavor a little bit, but it doesn't create the flavor. Did the computer create this beauty? Well, the computer plotted this quickly, but all the computer is doing is indicating which points do or do not belong to the Mandelbrot set. The computer doesn't determine that. The laws of math determine that. Remember, we checked the first 2 points manually. We went through that formula and did it, and it was tedious. Remember that? Yeah. Theoretically, you could do that for all of these, and you could shade it by hand. It would take forever, but you could do it. The computer didn't create that. The beauty was already there. Did people make this? Well, people can't make something that's infinite. It's not like somebody sat down and said, I'm going to make this heart-shaped feature and draw a circle here, and then I'm going to draw an infinite number of babies. You can't do that. You don't have the time. Human beings did not make this. Human beings were surprised to discover this. The beauty apparently is built into math. The computer just reveals it. Well, likewise, what causes the complexity in fractals? The fact that they have these mathematical properties, the fact that they can add and they can count, and you have the powers of 2 and so on. Did the computer create it? Well, no. The computer simply allowed us to see it quickly. A computer doesn't create a fractal any more than a microscope creates bacteria. The microscope allows you to see bacteria that you couldn't otherwise see. The computer allows you to see this shape. It doesn't create it. The shape's already there in math. And remember, we checked the first few points manually, and we found that, and mathematicians have proved that that the main cardioid of the Mandelbrot set, it is true. It's not an artifact of the computer or anything like that. When these were first discovered, they thought maybe there's a glitch in the computer that somehow resulted in that. But we now know that's false. These shapes exist. They're built into math. The computer didn't create it. It just plotted it. It allowed us to see it, and it did so quickly. Did human beings create it? Well, again, we can't create something that's infinite. Things that human beings create, when you zoom in on it, they get more simple. They don't get more complex. Did the formula z squared plus c create it? Well, it determines the shape, to be sure, but we found that when you change the formula, you still get beauty and complexity. So the formula by itself is not responsible for it. It does determine the shape, to be sure, but we had to feed numbers into that formula to get that shape and see what happened. Apparently, the complexity is built into math. It's built into numbers and the relationships between numbers. So I'm going to ask, what is math? That sounds like a silly question, but mathematics is the study of the relationship between numbers. That's the dictionary definition. And so then you know what I'm going to ask. I'm going to say, well, what are numbers? Oh, well, Dr. Lisle, we know what numbers are. Can you define them? It's interesting. These concepts that we take for granted, we rarely think about. How would you explain it to somebody that knew nothing about the topic? How would you define it? The best definition I've been able to find in the dictionary is that numbers are a concept of quantity. I think that's a good definition. Numbers are a concept of quantity. Quantity is how much of something you have, and numbers are a concept of that. So when you're thinking about quantities, when you're thinking about how much of something, you're thinking a number. Now, since numbers are concepts, they are by nature abstract, not physical. You cannot touch a number. You can't taste one because they're abstract. They exist in the mind. There's the number 3, for example. Now, but is that really the number 3? Because if it is, I just destroyed the number 3. And children will now have to count 1, 2, 4, 5, and so on. Because you said that was 3, and I destroyed it, so there is no more 3. That wasn't really the number 3. That was a representation of the number 3. And removing the representation does not remove the number 3, right? Written numerals are not numbers. They're representations of numbers. And human beings have decided that that particular shape will represent 3-ness. And if you're Roman, you know 3 vertical lines represents 3-ness. We can pick different numerals. So you can have Roman numerals or Arabic numerals. I understand that. But that simply represents numbers. Numbers exist in the mind. Laws of math are conceptual. They exist in the mind. But where do laws of math come from? How do we account for them? Because, I mean, you know, like the Pythagorean theorem or things like that, or the commutative property of multiplication, where do these laws come from? Now, because we're trying to account for this incredible complexity built into numbers, so where does this stuff come from? Now, the way that secularists will explain complexity in the physical, biological world is evolution, right? They'll say, well, granted, something like, like a human being couldn't just, appear, but life didn't start that way. Life started very simple, and that's easier to get by chance. And then gradually it evolved to become more and more complex. Now, I would reject that for good reasons. But did laws of math evolve? See, that's a non-starter when it comes to math, because numbers don't change. It's not like 7 used to be 3, but then it evolved, right? Numbers don't change. They are what they are. They're fixed. Laws of math do not change. It's not like triangles added up differently before Pythagoras discovered, the theorem or a way to prove that particular theorem, right? They still added up the same way. Laws of math have always existed. Were they created by people? Some people think so. I mean, there you go. Pythagoras, he invented the Pythagorean theorem. Well, actually, he didn't, but he found a way to prove it. But it's not like triangles added up differently before Pythagoras. They still added up the same way. People simply hadn't discovered it. Human beings do not create laws of math. We discover them. And sometimes the laws that we discover are counterintuitive. I remember the first time I was shown how to integrate a Gaussian from negative infinity to positive infinity, and the proof was beautiful. It was just stunning. It's not something that we would have created. It's something that we get to discover. Do laws of math come from the universe? No. Now, interestingly, the universe does obey laws of math. But math goes beyond the physical universe. The physical universe is, for example, 4-dimensional. You get the 3 dimensions of space and 1 of time. And perhaps there are other dimensions if you believe certain theories of quantum physics. But math can have an infinite number of dimensions. You can have any dimensions you want. That was one of the things that I learned in one of my calculus classes was if you had the 4-dimensional equivalent of a sphere, it's like a sphere is 3-dimensional. What would a sphere be like in 4 dimensions? What would be its hypervolume? And how to calculate? You can use calculus to calculate that, and it's meaningful. Math goes beyond the physical universe. So it doesn't come from the universe. I'm going to suggest that laws of mathematics stem from the mind of God. Math is the way God thinks about numbers. And so when you're studying math, in a way, you're doing theology. I wonder if students, if they realized that, if maybe they would look at math a little differently. Might be something to think about. Because think about what laws of mathematics are. I mean, when you think about a law of mathematics, like the commutative property of multiplication, it's conceptual. It exists in the mind. It's universal, meaning laws of math apply everywhere. It's not like they apply in this room, but you go next door, 2 + 2 might equal 7, right? I mean, that one doesn't make sense. The laws of math work the same everywhere. They're invariant, meaning laws of math do not change with time. It's not like, yeah, 2 + 2 = 4 on Saturdays, but on Thursdays, hey, they might equal something very different. I mean, that would be absurd. And they're exceptionless. It's not like 2 + 2 = 4 most of the time, but every now and then 17. And if you think about it, the properties of laws of math make sense if indeed they are reflections of the way God thinks about numbers. Because of course they're going to be conceptual, because God's thoughts are conceptual. All thoughts are, right? Laws of mathematics will be universal because God is omnipresent. His power is immediately available everywhere in the universe. And so laws of math will work equally everywhere in the universe. Laws of math don't change with time because God doesn't. I, the Lord, do not change, therefore you sons of Jacob are not consumed. That's what the Bible teaches. And so, of course, his thinking is not going to change with time. And laws of math are exceptionless because God is sovereign. There's no truth outside the mind of Christ. Colossians 2:3, all the treasures of wisdom and knowledge are deposited in Christ. So the Christian can make sense of this. The Christian can say, wow, when I look at fractals, I'm getting a little window into how God thinks about numbers, and it's beautiful. And I can appreciate that beauty because I'm made in the image of God, and I can reflect in a finite way. I can reflect God's character, and I can appreciate that beauty. But what about a naturalist who believes that there's no God, nature's all that there is? He's got a problem. Because laws of mathematics are conceptual, meaning they exist in a mind. That's where they live. You can't stub your toe on a law of mathematics. You can't accidentally swallow a law of mathematics or pull one out of the refrigerator. They exist here in the mind. But wait a minute, the naturalist has a problem because laws of mathematics existed before people. The way the planets orbit the sun, they obey mathematical laws. Kepler discovered these. He was a creation scientist, by the way, devout Christian. He discovered that the period of a planet squared is proportional to its distance from the sun cubed. P squared equals A cubed. Law of mathematics. But here's the thing. They orbited that way before people for 2 days, but still. In the secular view for billions of years before people. So, but laws of math require a mind. Planets obeyed laws of math before human minds existed. You have to have a mind before people. You see the problem? The naturalist doesn't believe in minds before people. They think the universe is by chance and that the human mind is something that evolved. You see the problem? There are also what we might call physical fractals. The fractals we've looked at so far are perfect fractals. They repeat infinitely and are only found in the abstract world of mathematics. You can plot them, but you have to use a computer to discover which points belong to a particular set. But the physical world also has things that are approximate fractals. When you zoom in on them, you get a smaller version of the original up to a certain point, and eventually it stops because you get down to the level of atoms, and you can think of them as little spheres, I suppose, or waves, depending on how you want to think of it. But there are many things in the physical world that are approximate fractals, such as snowflakes. Snowflakes are fractal. You zoom in on a snowflake, the whole thing looks like this six-figured shape, and you zoom in on it, you get a smaller six-figured shape, and so on. It may not repeat exactly, but the smaller structure looks similar to the original. Scale invariance, that's what it means to be a fractal. You get a smaller version of the original. So these little gems from heaven that the Lord sends us, and I don't know if you get them too much down here, but in Colorado, we get a lot of these little gems from heaven. And you scrape them off your car, but they're actually quite beautiful when you look at them. They're stunning. I remember even growing up in Ohio, sometimes when the weather was right and the humidity was right, you get this stuff that grows on your windows and it forms these beautiful fractal shapes. That's the way that ice forms. It forms these fractal structures. Ferns are fractal in nature because they have a central stem which branches, and then the branches branch into branches, which branch into smaller branches, and eventually you get down to the little leaves. But that is fractal. And amazingly, I even found a form of fractal broccoli. So I guess broccoli is good for something after all. It's called Romanesco broccoli. It's actually related to a cauliflower, amazingly. But if you zoom in on it, the whole shape is kind of like a cone, And it's made of smaller cones, which are made of smaller cones, which are made of smaller cones. Isn't that fascinating? The way coastlines branch is fractal. So they branch and they branch into smaller branches, which branch into smaller branches. The way mountains branch from above, the way the valleys branch, they branch into smaller branches, which branch into smaller branches that resemble the whole thing. Clouds, the way clouds divide is fractal. They break into smaller clouds, which break into smaller clouds. The way lightning branches is fractal. It branches and then branches into smaller branches, which branch into smaller branches, and so on. And you can see that in real time with super slow motion capture cameras. Look at that. Until the leader connects, and then most of the current goes down the leader. But really amazing. So here's my question then. Why do fractals occur both in math, which exists in the mind, and the physical world, which exists outside the mind? Math made of thoughts, physical world made of atoms. I mean, this particular shape, that's a mathematical graph. That's a multibrot. That's z to the 7th plus c. That cannot be found in nature, but that can. We get a lot of them in Colorado. That shape right there, part of the Mandelbrot set, you can't touch that. That you can, although you shouldn't. Okay? This particular shape, you might say that's a plant. It's not. That's a mathematical graph. It's called a Barnsley fern. And a Barnsley fern is a mathematical structure where each leaf is the entire shape. Let me show you. You can take the entire shape and reduce it down to one leaf. See? Let's do that again. You can do that forever. Isn't that amazing? So that's a Barnsley fern. It's a mathematical graph. You can't touch it, but that you can. This particular shape doesn't exist in the physical world, but that does. It grows on your windows sometimes when the temperature conditions are just right. This particular shape, it's a mathematical graph. It does not exist in the physical universe. This, unfortunately, does. That's a mathematical graph. It's part of the Mandelbrot set in the Valley of the Double Spirals. You can't see that in a telescope, but that you can. It's the Whirlpool Galaxy. I've seen it myself. So why is it that fractals occur in the abstract realm of math, of thought, and also in physical nature? Now, one answer is that the physical universe obeys mathematical laws. And that's not bad as far as it goes, right? I mean, the physical universe obeys math. Math can produce fractals, therefore the physical universe can produce fractals. I like that answer. It's good, but it leads to another question. Why does the physical universe obey math? Math is something you think. Why does the universe care about what I think? Well, it really doesn't, but it does care about what God thinks. When I think math, and when I'm doing math properly, I'm thinking God's thoughts after him. And whose mind is it that controls the universe? God. And so I can make sense of this as a Christian, that that mathematics is a reflection of God's thoughts, and the universe is upheld by the mind of God. According to Scripture, God upholds all things by the word of his power. Christ, in particular, it's the Son that upholds the universe, and in him all things consist or hold together. And so I can make sense of that. It's the mind of God that controls physical reality. Math occurs in the mind of God. Math will occur in physical reality. But the secular worldview cannot cogently answer this. They cannot explain why the laws of math have the properties that they have, why laws of math are conceptual, universal, invariant, exceptionless, or how they could possibly know. How could you know that the laws of math are universal? Do you have universal experience? How do you know they work in the Andromeda Galaxy? Have you ever been there? You have not. Now, somebody could turn that around on me and say, well, how do you know they work in the Andromeda Galaxy? I could say, because God upholds the Andromeda Galaxy, and God's told me that, right? I have this great book. It's a bestseller. It's written by God. How do you know how God thinks? He told me. He's written a book. You can read it too. The secular worldview cannot explain why the physical world obeys laws of math. They can't. And I want to show you this. There's a wonderful article written by Dr. Eugene Wigner. He's a PhD physicist. He's a brilliant guy. He won a Nobel Prize in physics. The guy is super smart, but apparently not a Christian, or at least he doesn't have a Christian worldview, because he wrote an article where he ponders this question: why is it that the physical universe obeys math? He says it is difficult in this article, it is difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and of the human mind's capacity to divine them. He's basically saying it's amazing enough that there are laws of nature. What's even more amazing is that we can discover them. And they happen to have a lot of them happen to form these nice, neat little equations like E equals mc squared. That's convenient. Or F equals ma, right? These formulae that the universe obeys, we can discover them, and a lot of them are simple. That's convenient. Why? Why does the physical universe obey math? Here's his conclusion. The miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. That's his, and I'm not making fun of him. The guy's brilliant. I'm just pointing out that on his secular worldview, he cannot answer that simple question, but everyone in this room can. The physical universe obeys math because math is the way God thinks about numbers, and it is God's mind that controls this universe. Of course, the universe would have to obey math. I can explain why I'm able to discover some of these things in the universe because I am made in the image of God, and God has given me the gift of rationality, the ability to think in a way that's consistent with his thoughts. I can't think infinitely like God can, but I can think in a way that's consistent with his character. He's given me reliable senses, so I can look out into the world, and the information that I get to my mind is basically truthful. Maybe not perfect because of the curse, and we are finite after all, but nonetheless, I have a basis for being able to do science and study it and find mathematical patterns in the universe. And of course, those Christians that embrace that have been very successful in discovering patterns in the universe. But the secular worldview is bankrupt. It cannot answer this important question. It doesn't work. Beauty of infinite complexity is built into numbers. Isn't that amazing? That's what we've seen this evening. Numbers are abstract conceptions of quantity, and concepts require a mind. Therefore, numbers require a mind. Numbers existed before people. A mind existed before people. The creation worldview can make sense of that. The biblical worldview can do that. The secular worldview cannot. Numbers are a reflection of the way God thinks. The secular worldview cannot account for the existence and properties of numbers or mathematical truths. We're often surprised when we discover some new principle of mathematics. The Greeks, when they discovered irrational numbers, they were shocked and they were disappointed that such numbers existed. They didn't want them to exist. That's proof that we didn't invent math. We could have made it a lot easier if we had done it, right? But math reflects God's thinking. And some children will say, yeah, but it's hard. Yeah, it's because you're learning to think like God. You think that's going to be easy? But it's beautiful. It's beautiful. Numbers existed before people, but they're conceptions, meaning they require a mind. I can make sense of that because I have a mind before people. The mind of God exists before people and before the universe even. Laws of mathematics are universal, invariant, abstract, and exceptionless entities, and that makes sense given the characteristics of God as described in the Bible. We've seen that the physical world also contains fractals, and the secular world cannot account for why the physical universe obeys mathematics, which would be what is necessary for the physical world to have things like fractals. But I can make sense of that because the universe is controlled by the mind of God. Isn't that cool? So I hope this is, if nothing else, given you a little bit more of an appreciation for the awesomeness of the mind of God, to be able to think that way, and to have had, and that was a little secret that only God knew until 1980. Isn't that neat? And now, a lot of us have played with fractals, and maybe you've got computer software that can do that. But anyway, we do have this presentation on DVD and also on Blu-ray, because as you can tell, it's very beautiful. So we put that one on Blu-ray as well. And we do have a book that covers this topic and goes into some things that I didn't get a chance to go into that are just fascinating. The history of this subject is just fascinating. So Fractals, The Secret Code of Creation. And if you get that book, it also comes with computer software where you can explore these shapes yourself. You can zoom in on them. In fact, the software contains all the pictures in the book, and one of the neat things about the software I wrote is you can take a previous picture and drop it into the program and continue to zoom in where you left off. So that's kind of fun. Or you can change the colors and things like that, and that's fun to do too. So Fractals, The Secret Code of Creation. This is all part of the conceptual scheme that I talk about in the Ultimate Proof of Creation, where I show that unless Christianity is true, you couldn't prove that anything is true. And we have that on DVD as well, Ultimate Proof of Creation. Understanding Genesis. It goes through some of the stuff that Marcus Ross actually pointed out earlier, that a proper hermeneutic will lead you to the conclusion that, yes, God really did mean that he created in 6 days, and that it was a few thousand years ago. And I won't go through all these. We covered these before. But this will be your last opportunity, especially with the packs, because the packs are only at this conference. So check out the book pack, the best of our books for 20% discount, our video pack, the best of our DVDs for 20% discount, or our library pack, the best of everything for a 30% discount. Don't forget about the children's resources as well, and sign up for a free monthly newsletter. So again, this little break that we have before the Q&A panel will be the last opportunity to get books from the Biblical Science Institute. My team's going to be packing up during the Q&A. So take this opportunity to get these materials, and check us out on the website as well, biblicalscienceinstitute.com. So thank you very much. God bless.